Hello everybody. In this lecture we're going to be learning about probability, Monte Carlo or stochastic programs, and statistics. It's just a brief introduction to probability and statistics, so don't expect this to be a replacement for a course on this topic, but there is a course in second year that you'll take that kind of expands upon these two topics. All right. So first of all, let's just do some very basic probability. If you're flipping a coin, assuming that the coin is fair, what's the probability of getting tails? You probably already know this based on something maybe you did in high school or just common sense, but let's actually work through the math and how you figure out this probability. It's a half because calculating it is that there are two possible outcomes, heads and tails, and only one of them matches our goal. So we're specifically looking for tails, so that's only one out of the two outcomes. So we put the number of outcomes that match our goal over the total number of outcomes, and that gives us the fraction that represents the probability of that outcome happening. Okay, so we use this terminology right here, P of t. So in this case, we just choose some letter that represents the situation. In this case, getting tails, we'll use the letter t. So probability of t is a half, or 0.5, or 50%. Okay, one important note, if we have probabilities of a bunch of independent events, it's important that those probabilities actually add up to 1. So for example, in this case, the probability of getting tails is 50%, 0.5, and the probability of getting heads, the only other possible outcome, is also 0.5. You add those together, you get 1. Sometimes we are not just concerned with a single event, we're concerned with multiple events. So assuming that the events are independent, and I'm going to talk about that in a second, then how should we figure out the probability of both of those events, or even multiple events, are occurring? So if you're not that familiar with notation from like Dungeons and Dragons or other role-playing games, a d6 is just a 6-sided die, the normal die that you've probably used before. So this question is asking, what's the probability of rolling 2 consecutive ones on a d6? So we can treat this independently. We can use the same kind of calculation to say, well, rolling 1, 1 has a probability of 1/6 because there are 6 sides to the die, 1 through 6, and only one of them is a 1. We're only interested in the 1. So there's one outcome that matches our criteria, and there are a total of 6, so 1 over 6. Rolling the second die similarly has a 1/6 probability of getting a 1. So rolling 2 ones in a row involves, first we have to roll a 1 on the first die, and then we also have to roll a 1 on the second die. And the way that we calculate the combined probability is multiplying the two probabilities together. And this sort of makes sense if you think about it, because imagine a situation where only 1/6 of the time I'm rolling a 1, and then I need to roll another 1. Well, 1/6 of those times I'm going to fail to, I'm going to roll a 1, and 5/6 of the time I'm going to fail to roll a 1. So we actually need to roll a 1/6 chance on the first one and a 1/6 chance on the second one, giving us a very low probability of 1 over 36. And there's nothing special about this being 1 and then a 1. This is the exact same probability if I were to ask what are the probability of rolling a 3 and then a 4 on a die. That has the same probability because rolling a 3 has a probability of 1 over 6 and rolling a 4 has a probability of 1 over 6. And these are independent. That simply means that the first roll doesn't in any way impact the second roll. So we're assuming again that this is a fair die and we're not influencing the second roll with the first one. Okay, so this is called the multiplicative law. It's pretty easy if you want to figure out the combined probability. We just multiply the probabilities together. All right, we could also work this out the old-fashioned way. We're probably not going to do this generally speaking, but give you an idea. Here are all the possible rolls. We could roll a 1 and then a 1, and then a 1 and then a 2, and then a 1 and then a 3. These are all possible, right? All the way from rolling a 6 and then another 6. There's 36 of these possibilities. We can count them, and only one of them matches the goal, so 1 over 36. The only one that matches the goal is rolling a 1 and then rolling another 1. All right. So we mentioned about if probabilities are independent, we can use the multiplicative law. If probabilities are not independent, then we can use something called the Bayesian rule. or Bayes' rule. And that's actually a beneficial thing for us to do because there are a lot of situations where probabilities of events are not independent. So you could say, for example, probability of having a certain symptom, like a runny nose, and the probability of having a cold are not completely independent. I mean, you can have a runny nose without having a cold, and you can have a cold without having a runny nose, but there's a relationship between the two, so they're not fully independent. So having a runny nose perhaps increases the probability that you have a cold, and vice versa. On the other hand, you might have a sports car, and getting a ticket, getting a speeding ticket, are definitely dependent events. I guess it depends on your driving habits, but if you have a sports car, you're likely to drive fast, and as a result, you're likely to get a speeding ticket. So those would be dependent events, but I would also say, having a cold and B is driving a sports car, then I wouldn't expect there to be any relationship between those two things. Having a cold doesn't make it more likely that you're going to drive a sports car, as far as I understand, at least my understanding of sports cars. And having a sports car doesn't necessarily increase your chance of having a cold. Maybe a convertible, but a regular sports car like a Ferrari probably doesn't increase your chance of getting a cold. So we represent conditional probability using PA/ pipe B. So A, vertical bar, B. And this simply means, what's the probability of A happening if we know that B has happened? So for example, we could say, what's the probability that I have a cold? That's what A stands for. If I have a runny nose. B is the probability of having a runny nose. Or B is the event of having a runny nose, and P of B is having a runny nose. So in situations that are independent, so for example here, A is having a cold and B is driving a sports car. A and B are independent events. So as a result, the probability of A happening, given that B has happened, shouldn't be any different than the probability of A happening, regardless. And so in that case, we would assume that it's going to be exactly equal to the probability of A. But if A is having a cold and B is having, say, a stuffy nose, then I would expect that the probability of A given B is greater than the probability of A. So in other words, the probability of having a cold is relatively low. The probability of having a cold if you have a stuffy nose should be greater. So it might still be low, but it's still greater than the probability of just having a cold, generally speaking. And that's because I don't consider events A and B to be independent. And this might be something we have to draw from our experience in subject matter. So for example, if we're analyzing things to do with viruses and symptoms, we'd consult medical and virologists and so on, experts, in order to determine whether or not these are independent events. We wouldn't just decide. It's not always common sense. It's very often you have to consult an expert. All right, so related to probability is something called stochastic programs, which actually sounds really complicated, but stochastic programs are quite simple. They're just programs that have an element of randomness in them. And a lot of the programs that we've been working on throughout this semester so far have been deterministic programs. And deterministic programs are elements that they're always going to produce the same output if you give them the same input. Stochastic programs often don't follow that rule. A stochastic program, because of the degree of randomness in there, they could perhaps behave differently from one execution to the next, even if the input data is the same. So you might refer to a stochastic program as a non-deterministic program. And there are lots of algorithms out there that are non-deterministic. We're going to talk specifically about one kind of stochastic program called a Monte Carlo simulation. And if you're familiar with what Monte Carlo is, it's a tiny little microstate in Europe where I think France kind of exiled their royal family. And Monte Carlo is pretty famous for having a casino, or multiple casinos. And so the reason why it's called Monte Carlo simulation has a lot to do with the fact that there's a casino in Monte Carlo. So you can kind of imagine that Monte Carlo simulations were created with writing programs to try to understand what happens in a probabilistic scenario, like rolling dice or dealing cards or flipping coins and roulette wheels and stuff like that. kinds of things that typically happen in casinos. Now, Monte Carlo simulations are not only useful for simulating what happens in casino games, but that's where they got their start. So imagine, for example, I want to write a program that's going to simulate the rolling of one die. And so we can actually work this out the way that we did earlier on in the slide by just saying, okay, well, I want to know what the probability of a 1 is. The probability of a 1, because there's only one 1 on the die, and there are 6 possible sides, one of which is the 1, then the probability of rolling a 1 is 1 over 6. And similarly for 2 through 6, those are all outcomes are all 1 over 6. And they all add up to 1, so everything is obeyed in our understanding of basic probability earlier in this lecture. And so we might just, approximate the 1 over 6 value and say, let's just say 0.17. The way a Monte Carlo simulation works is if we want to simulate the rolling of a die, we want it to behave differently, right? So if we want to check to see if the die rolled as a 1, I would expect that 5/6 of the time it's not going to be a 1, and 1/6 of the time it is going to be 1. So what we can do is we can generate a random number, and if the random number falls in the range of 0 through 0.17, then we can say they rolled a 1. And then if it falls in the range of 0.17 exclusive all the way up to 1, the random number is between 0 and 1, then we can assume that we rolled one of the other numbers, 2 through 6. So it might look like this. Basically, this is just sort of pseudocode. We've got generate a uniform random number in the range of 0 to 1. So R is our random number, and it's in between 0.0 and 1.0. If R is less than 0.17, then we consider the roll to be a 1. If R is less than 0.34, remember these are mutually exclusive, so this means that it's greater than or equal to 0.17 and less than 0.34. Now we would say that the roll was a 2, and else if the R value is greater than or equal to 0.34 but less than 0.51, then the roll was a 3, and so on. So these are, where do I get these numbers from? Well, 0.17 is just the value that we figured out based on the probability of rolling a 1. It was 1/6 probable, and so therefore the 0.17 comes from there. And then 0.34 is just in between the 0.17 that we used for the 1 and the next 0.17. So we just say 0.17 plus 0.17, and that gives us 0.34. And then similarly, we add another 0.17 to get the next range. So between 0.34 and 0.51. And then the next one will be 0.68, and so on and so forth. So we can actually write some very useful programs this way. So for example, I want to deal a card. I can generate a value between 0 and 1, and I want to determine which card it was. Well, there's 52 cards in the deck, so there's no jokers or anything like that. Then we could just say, if the number is between 0 and 1 over 52, then it was a 2 of spades or something like that. You could just assign ranges to every possible outcome. Or another way to do that same thing would be to generate 2 random numbers, and the first random number would determine which suit. So we would have a 0.25 chance for each of the 4 suits in a deck of cards. And then we would also generate another random number for the numeric value, and that would be, in that case, 1 over 13. So 1 over 13 chance of it being a 2, 1 over 13 chance of it being a 3, 4, 5, etc., all the way up to a king. Or an ace, actually. Forgot the ace. All right, so one kind of Monte Carlo simulation is a random walk, which in its own right is useful. So we'll typically use Monte Carlo simulations for all kinds of things. Monte Carlo simulations, for example, are being used pretty heavily these days. Especially during COVID, we were talking about the possibility of spread of the disease. In that case, they had some numbers based on how likely you were to contract the disease if you were in contact with somebody who was contagious at the time, and how close you were, and whether people were wearing masks and so on. They figured out all of these numbers. And then what a lot of people did was they created some Monte Carlo simulations of people going to class or going to church or going grocery shopping, going to work and interacting with customers, and then determine the likelihood that the disease would spread. And they, presumably they prioritized certain businesses to stay closed during the most significant times during the pandemic in order to reduce the spread of the disease, but also give people as much freedom as they could without putting them at too much risk. So a random walk is a different kind of Monte Carlo simulation. And I'll explain why it's a Monte Carlo simulation in a minute, but let's just describe it. In the MIT lectures in the artificial intelligence course, they talk about it's an MIT student, but I'm just going to say a drunken bar patron is walking home. And imagine the scenario that they're standing in a certain spot and they have a likelihood to step in any direction. Just to keep things simple for right now, we could just say, let's say that they can only step in 4 possible directions. So they're kind of walking on a grid, which isn't particularly realistic, but we could add more directions. For example, we could have an 8-way directional choice that they could make, or even greater than that. But let's say that there's 4 choices. They could take a step forward, they could take a step to the right, they could take a step backward, or they could take a step to the left. So this is a Monte Carlo simulation because we could just generate a random number. The number is between 0 and 0.25, let's say, they go forward. If it's between 0.25 and 0.5, then they go to the right. If it's between 0.5 and 0.75, they go backwards. And if it's between 0.75 and 1.0, then they go to the left. So a random walk just repeats this. So every step is done in a Monte Carlo way. We generate a random number and determine which direction they're going to take a step. And then the question is, where do they end up? So random walks are actually used in a lot of different situations, including simulating Brownian motion, the motion of particles floating through the air, particles floating through any kind of fluid, including water. If you watch, dust particles floating around in your room after nobody's moving around anymore, they kind of follow this Brownian pattern. A random walk could be used to kind of simulate that. All right, so to answer the question, where do they end up? As it turns out, a random walk is a little counterintuitive in this way. You might imagine that since there's an equally likelihood for them to go forward and backwards, and there's also equal likelihood that they're going to take a step to the right and to the left, then they'd end up basically where they started, right? Because half the time they would go forward, and half the time they would go backward, and half the time they would go right, and the other half they would go left. But as it turns out, they usually end up farther and farther away the more steps that they take. And I guess that would be true, that generally they would stay close to their origin point if we were only simulating in 1 dimension. But because we're simulating in 2 dimensions, once we go to the right, it's not just a matter of it's just as likely to go back to the left, because it's not. It's actually just as likely for them to go to the left or up or down or to the right. And if they go up or down or to the right, then they end up even farther away from the origin point. If they go left, they go back to the origin point. But if they go up or down, they're farther away. And if they go to the right, they're even farther away. So as it turns out, in 2 dimensions and 3 dimensions and higher dimensions, a random walk typically wanders far away from the origin point. But the path that they take, being somewhat random, is useful for modeling certain situations. As an example, when I was doing my master's thesis back in the day, I was doing some simulations on whether it would be efficient to use a certain network protocol in multiplayer games, although I called them simulations because at the time it was very unpopular to talk about video games in research. And so I did these interactive simulations, quote unquote, and it involved the person walking around in the game world and potentially interacting with one another. The first round of simulations that I did was they would just use a random walk, and they would basically just walk in random directions, and sometimes as a result, the simulated players would be near each other, and using that protocol, which is more efficient for sending messages to a group of nearby participants, would be beneficial. And if they're separated from each other, they don't really need to see any information about each other because they're too far away to even interact with one another. If they're playing a game, they're too far away from each other to shoot each other or even see each other's animations. All right, so here's some examples of things that we can simulate with random walks. Motion of bacteria at the microscopic level. most of the really small organisms are basically at the mercy of whatever fluid they happen to be floating in. Sorry, just a little bit of noise in the background. Sorry about that. All right. The effect of random mutations on a genome. This requires a little bit of thought because we're not actually talking about legitimate motion. We're talking about how things might mutate in various directions. These would be proteins that would be mutated as a result of, for example, various kinds of radiation. Proportions of nucleotide bases. Anyway, so I mentioned the motions of entities within an interactive simulation, quote unquote, game. That still persists today. Even at Ontario Tech, we have a course called Interactive Media, which is really basically about game development. Anyway, motion of users within a mobile network could also be useful for simulating various kinds of protocols for managing that network and handing people off from one cell tower to another. The motion of animals in an eco simulation, such as a predator-prey simulation. So it might have predators moving around. They kind of move around randomly until they get close to a prey animal, and then they try to hunt that prey animal in a certain proportion of likelihood that they might actually catch the prey. And if they don't catch the prey, they've expended energy and put their lives at risk, but they didn't gain any energy from consuming food. And so the prey has a greater chance, therefore, of going on to reproduce because it's still alive, and the predator has a smaller chance of going on to reproduce. These kinds of simulations are actually really, really common right now for introducing changes. For example, if there's cutting in a forest, such as in the Amazon rainforest, we want to see what the effects might be, or if there's a massive die-off of a certain population of creature or tree, we want to see what the outcome might be. For example, I lived in BC for a long time, and BC is currently suffering from an infestation of the pine beetle, and a lot of pine trees have died out in BC, and so there's just these huge forests that are basically just filled with dead trees. And there were a lot of people in those universities near there that were simulating that to try to see what the effect might be for grizzly bears and so on that tended to live in those forests, and the situation wasn't really good. And clearly it was true because we saw a lot of bears when we lived there. They were all kicked out of their forests, I think, and looking for garbage and stuff. Anyway, so we kind of answered this question in the course of the discussion. The walker would end up farther and farther from the origin. It is a little bit counterintuitive, but if you think about it in terms of the possibilities, when we're sitting on a particular spot, let's say I choose an arbitrary decision. Let's say, for example, I move forward. On the next step, the only choice that brings me back to the origin is to go backward. So going right, going forward again, or going left, those would all bring me even farther away from the origin. And so the probability is definitely against this walker ending up close to the origin. Certainly it is possible because it was random. Anything could happen with random. Probability always allows for things like that to happen, but it's very unlikely given enough steps that they will end up close to the origin. Okay, so I want to finish up this discussion by talking a little bit about statistics, which is actually, and we'll figure out how to use statistics a little bit in order to determine how to analyze some data. And again, you're going to follow up on this. There's a course on statistics and probability that you're going to take, but this is basically just meant to be a rough introduction. And then in the demo this week, we'll probably do some Monte Carlo simulations to help us practice with probability. But anyway, let's learn a little bit about statistics. People very much misunderstand statistics, and for the large part, they also kind of misunderstand probability and logic. I'd say those are the three things, the three math concepts that the general public doesn't really have a good, strong handle on. And I have conversations with people all the time that use, logical fallacies, or they use statistics incorrectly. So this is kind of an important thing, not just for computer scientists, but just being a good member of society, understanding what statistics are all about, because statistics can be used in ways to convey messages that are actually false. It's important to understand how those methods work and whether or not they are legitimate. So let's talk a little bit about terminology first. So first of all, I want to talk about the population. So population is basically everything. So one of the things we might consider is we want to vote in a federal election. So there's a call for a federal election, and the entire population of Canada is the population. But obviously, if we want to draw conclusions about what's going to happen in this election, we're going to not call every one of the 35 or whatever million people in Canada. They're going to take a sample. So they might say, let's call 2,500 people. And it's important to make sure that the population that you call, your sample, represents the population at large. So, for example, if 38% of Canada's population is people aged 65 or older, you have to make sure that 65% of your sample are aged 65 and older. And you have to make sure that all the demographics are represented. So you got to make sure that you have religious representation, ethnicity representation, LGBT representation for everything needs to be included in your sample for your sample to accurately reflect the population. Because you can kind of imagine a situation where you might have a population which is very diverse, and then you take a sample which is just white males over the age of 50. I don't think you can trust that sample result in predicting how the federal election is going to go, because certain demographics tend to vote a certain way. Another important thing about statistics to note is the null hypothesis. If you're trying to prove something, then the null hypothesis is basically the opposite of what you're trying to prove. So that you hope that the null hypothesis is false. So null hypothesis is represented using H sub O. In this case, or sub-zero. This is saying that really there is no effect whatsoever. That's what the null hypothesis is saying. So imagine, for example, I develop a new pill for something. And as it turns out, if using the pill is considered X in this case, to treat the disease, let's say Y, the outcomes are exactly the same as if we just gave those patients a placebo. The null hypothesis, therefore, is saying that our drug doesn't work at all. So the null hypothesis in that situation is our drug isn't working at all. So if we're trying to prove something, we can't really prove it beyond the shadow of a doubt. What we can do is we can show that the null hypothesis is extremely unlikely. So we can say something like, well, in order to get the data we did, the probability is something like 3% likely for us to get that data. And even then, somebody might say, well, I'm going to replicate your experiment and see what happens. And if they also get like 3% or 2%, then that sort of adds weight to your assumption that the null hypothesis is false. But if they get something like 50% and you got 3%, then maybe the null hypothesis is true. So the null hypothesis is something that you're hoping is not true. You have to consider it. So remember that a scientist has to be objective. And if you want to see if your hypothesis works, it's called your alternative hypothesis. And in the case of the development of a new drug, we want to show that using drug X to treat disease Y has a statistically significant and measurably better outcome than a placebo does. That's what we want to show. We can't actually show that it is 100% true. We can just say that the likelihood is very true. So that's where we end up getting this null hypothesis. So let's talk about the mechanisms that we can do in order to do that. Let's talk a little bit about more terminology. First of all, mean. You probably have already calculated the average. But the mean, of course, is just the sum of all the values divided by the number of values. And you've probably calculated an average before. Certainly, we've had to do it in this class. Another similar concept is the idea of a median value. So if we took all the values and we sorted them, the median value would be the middle element, if we had an odd number of values, or it would be the average of the two middle values if we had an even number of values. And oftentimes, the two middle values end up being the same value. So the median value is either one of them. And we also have the mode, which is the most frequently observed value. These things don't have to necessarily be related to each other. We can often have very different means and medians. We can often have very different modes and means. They don't necessarily have to be consistent with one another. If, for example, I have a mean in my class of 65%, that's pretty normal for a university course. If this was a final exam or whatever, a mean of 65% is a sensible value. But then if the mode is 100, meaning most people in the class, the most common grade that people got was perfect score, then that just means that we have this strange distribution of grades where a lot of people got perfect. And in order to counteract that, to keep the mean low at 65%, that means we must have had a lot of failures. And really what we want to see is we want to see a nice bell curve, which we're going to talk about that in a little bit. So these values can sometimes use together tell us quite a lot about what happened with the data. Like, what is the nature of the data? All right, so first of all, I want to just talk about one thing first, since we're talking about how people think they're really poorly when it comes to statistics and probability. So this one's related to probability, but it's called the gambler's fallacy. And people use this not just while they're gambling. They use this in all sorts of ways in life, and people will drive down the street and hit a red light, and then they hit the next red light, and they're like, but I just had a red light, as if somehow the other light somehow affected the current light, which in bigger cities like New York City, it does work that way, but it doesn't work that way around Oshawa. So somebody might say, well, I'm playing a role-playing game, and I haven't rolled a 7 in a while, so I'm going to try to roll a 7 because the likelihood is greater now that I haven't rolled a 7 in a long time. And of course, that's silly. Or if you're betting on lottery numbers, you might say, well, 42 hasn't come up in several weeks, so I'm going to pick 42. Well, that's silly because those numbers are chosen at random, and there's no greater likelihood of rolling a 42 this week than there was last week. All right, so for independent events, subsequent trials are not impacted by earlier ones, like die rolls and coin flips and card deals and stuff like that are generally independent. Card deals are and also aren't. So if you consider like Las Vegas or Monte Carlo card deals, they usually have something like 5 decks of cards. So if you get dealt a card like Queen of Spades, for example, there's more Queens of Spades still in there. And so you taking that card doesn't make it really that much less likely for you to get a Queen of Spades again. However, it does make it somewhat less. Okay, so I will just clarify, something like a coin flip or a die roll, those are 100% independent, and card deals are actually dependent. Especially if you're dealing from one deck of cards. If you're dealing from one deck of cards and you're looking for a specific card, and that card's already been played, there's 0 probability of you encountering that card again, and so therefore it's very relevant. These are dependent events. As I said, in casinos, they tend to use 5 cards or more, 5 decks of cards or more, and the probabilities are less noticeable but still dependent. All right, so one of the topics I want to talk about is variance, and it's represented using sigma squared. Sigma is this letter right here. It's the Greek letter, well, one of the Greek letters for S. And so I'll explain why it's sigma squared in a minute. But the variance is basically a measure of how spread out the values are. And so if the values are too close together, then that could be a representation that there's the way that we're measuring or the actual concept itself is not as diverse as we originally thought. So for example, if I measured the variance of grades for a final exam, I would expect there to be a significant variance in those grades because some people are going to get close to perfect on the final exam or perfect, and somebody else is going to get a very low score on the final exam. I would expect those values to be fairly spread out. Not too spread out because they can only spread out by 100 at maximum, right? The lowest score being 0 and the highest score being 100, assuming there are no bonus marks. So variance is a way to measure how spread out those values are, and it's a relatively simple calculation. I can kind of walk you through this. There's one more Greek letter that I should explain here. So this letter right here is a mu, kind of looks like an M, or kind of looks like a U actually, but it also kind of looks like an M. This is the Greek letter mu, and mu is basically just the letter M in the Greek alphabet, and M is short for mean. So there's a reason why all of these letters are the way they are, and so sigma, I'm going to explain to you what sigma is, because sigma stands for the standard deviation, which starts with S. So they use a Greek letter that's an S Greek letter, and then we use mu for M because M is short for mean. So basically, to calculate the variance, what we do is we're going to, for all the values x that we're trying to consider, we figure out what the square difference of x and the mean is. So first we calculate the mean, but then we calculate the square of the difference of how different each value is from the mean. We add them all together, all of those squares get added together, and then we divide by the number of values. So this is the average square difference for all of the values. That's basically what the variance is. And the reason why we square it is because by squaring it, we're creating a greater difference between these values. So instead of being a subtle difference, it's a more extreme difference. And this is actually going to bring the values closer together for a very small difference between x and mu. And it's going to bring the values farther apart for a larger difference between x and mu. Because fx and mu are very different, and the difference between them is great, and the square is therefore a larger value. But if the difference is less than 1, then squaring it will actually make the value smaller. Anyway, so that's sigma squared, or the variance. And then the standard deviation is a very closely related concept that is basically just the square root. And the standard deviation also tells us the same kind of information. It's a little bit more complicated to calculate. Notice the formula is exactly the same, except this is inside a square root symbol. So we take the square root of the variance in order to figure out the standard deviation. But the advantage and the reason why we use standard deviation more than we use the variance is because the variance just produces some value that has to do with the square of the various values that we're computing. So for example, if all these x values are final exam grades, then the relationship, the size of the value of the variance is going to be related to the square of those grades. And I don't know if that's necessarily a meaningful concept. So by taking the square root of the result, then we're scaling everything so that it has the same range, the same types of value as the values themselves. So in this case, the standard deviation is like in percentage values. If all the x values are values from 0 to 100, then we would expect this sigma value to compute to about a value between 0 and 100. And that gives us a good basis for comparison. So if I know that the standard deviation is, say, 20 on a final exam, then that gives me an idea of how far away the good grades and the bad grades are from that mean. Okay, and we will we'll talk about that in a minute. All right, so let's talk about numeric distributions. I'm only going to talk about 2 because there are 2 really interesting ones, and there's one really interesting one out of these 2. Okay, so the first one is a uniform distribution. And when we were talking about Monte Carlo simulations, I was assuming that the random numbers that we were generating would be pulled from a uniform distribution. That means that any value is equally likely. So if I generate a random number between 0 and 1 from a uniform distribution, then I'm just as likely to get 0 as I am 1, just as likely to get 0.57 as I am 0.0, and so on. All the values are equally likely. A Gaussian distribution is used, often called a normal distribution, but a Gaussian distribution is used when there are certain values that are more likely. And there are a lot of values that typically fall into Gaussian distributions. A pretty good example would be the height of a human. And so, for example, this might be, this chart might represent various humans. And then if you look along the x-axis here, we have a likelihood of 50%. Maybe this is the average height, and then so maybe this is something like 160 centimeters or whatever, approximately average height for a human. And you can see there's a lot of people who are in that range, generally speaking, really close to 160 centimeters. There are a lot of people who are at 170 centimeters and 180 180 centimeters. There are also a lot of people who are close to 150 centimeters or 140 centimeters. But then when you get down to here, something like 80 centimeters is less likely, and 20 centimeters is almost zero. And similarly over here, we could say something like the likelihood of somebody being 230 centimeters, it's possible, but it's a really small proportion. And then the possibility of somebody being 300 centimeters is almost zero. It's very unlikely. Okay, so this actually happens in practice quite a bit. A normal distribution is one of the most common distributions out there. And you're going to see this for all kinds of things in nature. But also, just consider astronomy, for example. There are average masses of stars, and there's this normal distribution that shows stars, and there are stars that are really, really massive, and then there are also stars that are not so massive. And then they follow this kind of distribution with this lump in the middle. We have far more likely things. So to contrast that with the uniform distribution, a uniform distribution would just be perfectly flat. All right, so in a true Gaussian distribution, then 68% of the values lie within one standard deviation. So if we measured the standard deviation to be 20, like the example I gave a minute ago, then from 50 to 70 and from 50 to 30, so if we consider the range from 30 to 70, which is a difference plus or minus 20, 68% of all the values are in there. And you can see there's a big lump in the middle, so that sort of makes sense. And then if we're willing to consider two standard deviations, so that would be 20 and then another 20. So that would be from 50 to 90 and also from 50 to 10. So from 10 to 90 basically, considering that as one big interval, 95% of all the values should be in that range. And if we consider three standard deviations, now these curves continue off basically forever in all directions, but definitely to infinity in this direction and to infinity in this direction. Three standard deviations would encompass 99.7% of all the values. So what we could do, if we want to have a certain certainty level, we could consider three standard deviations of information. That way we can be certain to 99.7 accurate. So this could be really handy, and we'll talk about that in a second. All right, so related to this is something called the t-statistic. And the t-statistic is really just something that you can look up in a table. And we often use this for things like comparing the null hypothesis. So imagine, for example, we do some experiments, and what we get probability-wise gives us some idea of how probable the null hypothesis is, or conversely, how probable is it that our drug is actually successfully treating the disease. Those are two related probabilities. They're opposite to one another, so the probability of the null hypothesis is just 1 minus the probability of the alternative hypothesis. So to calculate the t-statistic, sometimes called t-stat, we can just say that t-stat is equal to the mean of some sample. So we're going to take some sample from the population. So because when I was talking about sample, I talked about a federal election. So let's say, for example, I want to figure out the t-statistic, and I want to calculate the mean of the sample. So I'm going to calculate, what political whatever affiliation they had. So what's the mean political affiliation in the sample, and how does that differ from the mean political affiliation of the entire population? And then we divide that by, if you remember, this is the standard deviation, which is something very easy to calculate. Just plug it into that formula that we saw a couple slides back of the sample data. And the sample data is finite in size. It's relatively small. We have all of the data, so it should be possible for us to do that. And then we divide that by the square root of the number of values in the sample. So if the number of values in the sample was 2,500, I think that was the example that I gave, then we'll divide by 2,500. That'll give us this t-stat value. All right, so let's try to figure out how this fits in. First, let me talk about the p-value. So it's related to the t-stat value. And the p-value is the probability of getting a value at least as extreme, even if the probability, even if the null hypothesis holds. So that means, like, it's possible. So imagine, for example, I had a whole bunch of people volunteer for the study, and they're all willing to take my drug to cure their disease. And it just turns out that all of them just happened to get better of their own accord. And so I got really unlucky with the sample, and it made it look, or really lucky maybe, depending if I'm trying to sell my drug or not. It made it look like my drug was really doing the job. But maybe the people got healthy in spite of the drug, and the drug wasn't really doing anything. So you can get any kind of outcome. This is all probabilistic. It's all kind of random. And so I don't know necessarily if my drug was the thing that made them feel better. I can't say that for certain. But if my sample size is big enough, then the probability should go down, right? The more people there are, the less likelihood there is that just out of chance, my drug didn't do anything for them, but they happen to get better anyway. So anyway, this has to do with the probabilities from the empirical rule. If you remember, we talked about 68% of the values in a Gaussian distribution tend to be within one standard deviation of the mean. So what we're going to do for the p-value is we're going to choose a threshold value, alpha. Again, got to use those Greek letters. So we're going to use the Greek letter alpha, which is the Greek letter for A. We're going to choose an A value that's small enough, because if it's too big, then we could be attributing more to our actual drug than it deserves. This is called the type 1 error. That means that really the null hypothesis is true, but we've rejected it because we chose a really large threshold that allowed for random chance to make it possible for the null hypothesis, even though it's true, to look like it wasn't. We also must choose that alpha is large enough, because if we choose that it's small enough, we might be setting the standard too high, and as a result, even though the null hypothesis is false, it may end up looking like the null hypothesis is true. This is called the type 2 error. So in practice, there's a lot of people who kind of stand by an alpha value of 0.05. This is like a 5% value. But it depends. In different situations, in different fields, they tend to use different values. But the value should be small, and I would say that 0.05 is probably the highest possible value that you should use generally. So how does this relate? Hopefully we can kind of understand how this fits in. So you can see here is a graph that shows a Gaussian distribution of some values. And some of our results are on this graph. We obviously didn't calculate an infinite number of, we didn't perform an infinite number of experiments, but based on the experiments that we did have, we got certain results. Okay, now this, the middle here is the mean. So you can see mu is being used here in the center. And then we have mu minus t, that's the t statistic. Mu minus t is going to be the position where we're going to expect all of the values. So if we're going to assume that we want a value of 0.95, we want the alpha value to be 0.05. That means that, so for the null hypothesis, we want the probability to be no greater than 0.05. Then that means that these two blue areas here are smaller than 5% of the total area of this graph. Okay, now obviously if we choose a different an alpha value, then the alpha value will result in even smaller areas, and that'll make the t value get greater. So it'll actually be over here somewhere, a little bit more on the left, a little bit more on the right, so that we comprise less of the area of this curve. Anyway, so that's how that goes. So the t value is actually just to tell you, where on this graph, on the x-axis, are we going to create the interval. So we have plus and minus t, and the minus t and the plus t are going to create an interval. With the greater value of t, the interval is going to widen, and with a smaller value of t, the interval is going to narrow, and therefore we want to choose a value that creates the separation in the appropriate spot. And the p-value is the area of the curve. So we're going to have the p on the left side, the probability of occurring on the left side, and the probability of occurring on the right side. We might be interested in, say, for example, if this graph represents the outcomes, we might only be interested in the p on one side or the other, because we might only be considering people who recovered completely, and they'd be on the end of the curve where they had positive outcomes. Okay, so actually it is possible. One of these uses so one of these, this example right here uses the SciPy library. So up the top you can see I'm importing the SciPy library. I'm calling it stats just for the fun of it. And we have a bunch of results. So I haven't shown those results, but we're going to pass those results. So we have experiment results. These are results where the person took our drug, let's say. And then control results. So these are the experiments where they didn't take our drug. They took a placebo. And then we give that to the t-test. So you can see there's a function called t-test _ind. And we pass the experimental results, the control results, and that gives us back a result. The result is actually a tuple, which consists of the t-statistic and the p-value. So we can get both the t-statistic and the p-value. So we can just do it in Python here. It's a really easy way in order to do it. So this is quite helpful. So you can actually really quickly just determine how effective your drug was by looking at this p-value now. So if the p-value is something like 0.11, then you could say, ooh, that's not really that good, not very convincing that our drug works. Maybe we need to go back and continue working on it. Maybe the dosage isn't quite right. If the p-value is something like 0.02, then that's very compelling. That's saying, well, there's only a 2% chance that this could have happened by accident. And so it's most likely caused by our drug. And so we can feel confident about this, especially if somebody reproduces this experiment and does another trial with another 2,500 patients or whatever, and the p-value ends up still coming out to a relatively low value, then you can be confident that it's your drug that's curing these people and not just a lucky sample from people who happen to get better. So that's one thing that you might want to do in statistics, and that's basically proving that what you're trying to do is succeeding. And this is basically how you do that. The t-statistic and p-value are crucial in that. Usually you will see in publications that they'll publish their p-value, and their p-value will usually be a small value, and they'll say a p-value of 0.03 or something like that. Another thing you might do with statistics is regression, which is basically using your statistic knowledge for prediction. So that was for testing a hypothesis. Now this might be for determining what the pattern is in some values. And so imagine I've got a whole bunch of values. We've got some experimental data. We want to create a function that's going to allow us to fit some future data. So if, for example, imagine I've got a whole bunch of house prices that have sold in the last year, let's say, I might create a predictor function, which is some function, some linear function or nonlinear function that allows me to predict the value of a different house, and the function can take different values as input, such as how many bedrooms does it have, how many square feet, that sort of thing. And the ability to create a predictor function, aka a model, will be particularly helpful. Now we're just going to consider linear regression in this case, which is the predictor function is going to be a line, the function of a line. So y equals mx plus b, instead of using like quadratics or cubics or whatever in order to model the experimental data. You probably will have more accurate prediction if you use something like quadratics or whatever, but it's a little bit more complicated how you calculate that. So let's talk a little bit about that. So one way that we can do this is to determine how wrong something is. So we can create something called an objective function, and an objective function is used to determine how much error we've got. And so in this case, we are summing all the values from all of the observations. So x is the number of observations. So these are basically houses that have sold. What was the price of the house? And here's a value that we predicted using our predictor function. And how different were they? And then we square the difference, just like we did, if you remember, with the variance. We square the difference because, again, we want to kind of stretch out these differences, and then it's much easier to optimize, especially considering we have floating point errors and stuff like that in our program. So this might be an example of an objective function. This is not the only objective function, but this one is called the least squares. And this one's going to square all of the errors, add all those squares up. And then what we're going to do then is we're going to find the line that has the smallest of these sums of squares. One of the things you have to watch out for is something called overfitting, and this is not just useful in regression, but also if you're training a neural network or whatever. Overfitting simply means that what we're doing is we're creating a predictor that best predicts what's going on in the sample data that we have, as opposed to a more general predictor. So for example, if we have a bunch of data about house prices, if we overfit our function, it's only really good at guessing those specific house prices that we already know. And real-world data, such as new houses being sold, don't necessarily fit to the same degree. They might fit somewhat, but they might not. So that's something to be quite careful of. If you overfit, then your predictive power is reduced. An ideal way to avoid overfitting is to train with different data in different situations and then test it. So you're going to train it with one data set and you hold back some of the data to test it with the other part of the data set. So you might train it on, say, 80% of the data, and then you can use the remaining 20% to check to see if it's correct. Okay. So one of the things that you can do is you can calculate the coefficient of determination, represented by an R, no Greek letter this time. And this is just a measure of how much in percentage of a value from 0 to 1, how much of the data is explained by the predictor function. So in other words, this is kind of a measure of how close we are to being accurate all the time. And we would never expect that this would be 100%, because the 100% would mean that we knew exactly what was happening. There's going to be some variation. You can imagine house sales. People sometimes really fall in love with a house and pay maybe a little bit more than they should, or nobody notices this particular house being on the market and it undersells. There's going to be some variation that doesn't fall perfectly neatly into our predictor function. It's going to be a little bit inaccurate, but our predictor function is going to roughly predict. So calculating regression is actually easy. I'm showing you two different ways to do this. One is using the SciPy library. So again, up at the top, you can see that I'm importing the SciPy library. And I have some data here, X and Y. And then to calculate the linear regression, I call stats.linregress. And linear regression simply creates a function of a line that approximates the data X and Y. So X might be, how many square meters a house is, and Y might be the price of the house. So this will create a formula which, given a number of square meters, it produces a Y value that is the price, the expected selling price of that house. So this might be useful for a realtor or something like that. It might not be linear though. You can probably imagine there isn't much call for like a 21 bedroom house. Somebody who's going to buy a 21 bedroom house probably has millions and millions of dollars, and so maybe the size of the house and the price of the house isn't related by a line. But for simplicity here, we're doing linear regression. So you can see the results of the linear regression includes the slope and the intercept of the line, because this is a linear regression. So the slope and the intercept are the two components that we need in order to calculate the line values ourselves. And there's also some other values. So you can see the R value that we were just talking about. This is the coefficient, and the p-val, and the standard error. So again, these are all giving us an idea of how far away the values were, just kind of analyzing how closely this line model is at representing it. The NumPy library, so you can see I'm importing the NumPy library up at the top, import NumPy as MP, can also be used in this way, and it can be used for non-linear as well, and you'll see how to do that. So if you look down here at the bottom line, we're saying np.polyfit. Based on the name, you can probably imagine that this is possible to do things that are non-linear, in fact. And so in this case, we can supply it with a different degree. So we're supplying a degree of 1, which simply means that this is a function that has x to the exponent 1 in it. And if we put degree 2, then this would be a function that had x to the 2. So in other words, that'd be a quadratic. And degree 3 would be a cubic, and so on. So polyfit can do other types of curves, but they can also do lines. So we're supplying degree 1 here, meaning we want a line. And the results for when you call polyfit with the x and y value and the degree of 1 are the slope and intercept that we need to create the line. We'll have to compute the errors and stuff like that ourselves because NumPy doesn't do that. There are some functions that you can use for that, but it doesn't do it all at the same time. So that could be pretty useful if you're ever looking for some predictor functions. You want to see what the relationship is between data. You could use this, for example, to predict your your final exam grade and feed it in your midterm grades and your assignment grades and so on. Could be interesting. All right, so that's it for this lecture. It's a relatively simple lecture. Some of the concepts are a little bit complicated, so you might need to go back and review some of these topics, but hopefully next time we'll have a pretty good understanding of the probability and the Monte Carlo simulations, because we'll do a little bit of practice in both of those two areas. All right, so that's all for now. Thanks, everybody. Bye now. See you next time.